people are dealing with more crosstalk challenges. Like you look at the density of the ASICs today, we're still state of the art, right? 1 millimeter or 0.8 millimeter pitch for a lot of the BGA packages out there. The current densities are just going up. A lot of customers unofficially are pushing greater than 3 amps per ball on a lot of these packages, while shooting 224G or greater through these SerDes coming out. So the fan out and crosstalk challenges, not just from a signal to power or signal to signal, but from a power to power, are just becoming really challenging.
Hello, everyone, and welcome to the Altium OnTrack Podcast. I'm your host, Zach Peterson. Today, we're talking with Ben Dannan, founder of Signal Edge Solutions, and Tyler Huddleston, SIPI engineer at Signal Edge Solutions. Ben Dannan has been on the podcast twice before, and folks in the audience will know Ben as a simulation and modeling expert. Now, PCB designers who work with memory interfaces like DDR4 and faster will know how difficult it is to achieve time enclosure at high data rates, often requiring hours or days worth of electromagnetic simulation time. Ben and his team have developed a new approach and software that operates on HDF5 files from Keysight ADS, and this compresses the analysis down to only a few minutes. So I'm very excited to talk to Ben and Tyler today. The tools and workflows shown in this episode represent the guest's engineering approach. Appearance on Altium Academy does not constitute an official product endorsement. Let's start the show.
Thanks for having us.
Hey, Zach, thanks.
Yeah, absolutely. So, Ben, you've been on the podcast a couple times already. I'm very happy to have you back. Last time we had talked to you, actually the first time, I think you were working with Steve Sandler and Heidi Barnes on step loads, 2000 amp step loads, and you were still at Northrop Grumman at the time. And I know Signal Edge at that time, I think, was more of a side hustle. And then the second time we had you on, it was after you had been awarded the prestigious Engineer of the Year award from DesignCon. And Signal Edge had become more of a full-time thing for you. So if you could, since we last talked, just tell us a little bit about what's been going on at Signal Edge Solutions.
Yeah, it's been, I don't know, roller coaster. I don't know if that's a good enough word, but it's been a ride. I keep telling people I need to get a bigger seatbelt. It's been awesome. What I was doing in Northrop, we just figured out how to scale it outside, and we've seen triple-digit growth year over year, and now we're 16 people.
That's awesome.
16 people, 16 engineers, just doing SIPI, NEMC, modeling, measurements, and simulation. And we're doing things that are enabling us to be faster than everybody else, provide better quality, and helping people, get their design shipped, and doing things at both at the PCB and at the advanced package level. Everything from 224G to 5,000 watt ASICs and below.
That's awesome. That's awesome. So I'm sure we'll discuss more of that here in a moment, but I want to introduce everyone to our new guest, Tyler Huddleston. Tyler, having not been on the podcast before, if you could give everybody an overview of your background and how you got into electronics and got involved with Signal Edge.
Sure. Yeah. So hi, everyone. Actually got into electronics by way of music. So my first degree, I went to UNLV. I got a degree in film. And like being in film, I had lots of free time because my homework was basically to watch movies and then write about, what I thought about it. So I spent a lot of my free time playing music, and I was in a few bands in Las Vegas, and we did some touring. And on tours, equipment would break, and I taught myself to repair it, and that got me into electronics. And so I went back to school for electrical engineering. When I graduated, I was hired by Northrop Grumman. I moved out here to Baltimore, and during that time, Ben was basically assigned to me as a mentor, and he started teaching me everything I know about signal integrity and power integrity.
That's a pretty crazy story as far as getting into electronics, because I always like to ask people that, because you hear a lot of interesting stories, and that's definitely one of the more interesting ones. So thank you. Ben, you mentioned a lot of growth at Signal Edge Solutions, and you're doing a lot with simulation and analysis, and I'm sure with direct measurement of a lot of client designs. That's, I'm sure, giving you a lot of time to identify some very important challenges in simulation analysis as you've been working with customers.
Yeah, that's a great question. And it's funny, the challenges are definitely not getting easier. People are dealing with more crosstalk challenges. Like you look at the density of the ASICs today, we're still state of the art, right? 1 millimeter or 0.8 millimeter pitch for a lot of the BGA packages out there. The current densities are just going up. A lot of customers unofficially are pushing greater than 3 amps per ball on a lot of these packages, while shooting 224G or greater through these SerDes coming out. So the fan out and crosstalk challenges, not just from a signal to power or signal to signal, but from a power to power, are just becoming really challenging. And it's becoming difficult to make sure that you're right. And so we're constantly looking at those problems. And we just did a DesignCon paper, both Tyler, myself, and a couple other colleagues, where we showed how to model and measure PDN-to-PDN crosstalk for this application. And we showed correlation to simulation, single-digit millivolt correlation. And we published that paper in DesignCon this year. And, we're doing new challenges, but the other challenges are boards are getting thicker. You look at the data center boards, and Zach, you probably see this, like we work with ATE, we work with a lot of customers, a data center, aerospace and defense. Boards are more than 3 millimeters. They're 5, 6, 7, and 10 millimeters now. And so it's insane. So you think about, okay, routing the signals on an HDI board for something like that is really not an issue. We know how to do that. We know how to route the structures and do high speed, transmission line design for those things. That's not the problem. It's managing our inductance in those thick boards. And so this is where we're looking at things like more advanced laminate systems and how to integrate those and where we place those. And there was another paper that, again, Tyler and I did with Qnity last year, and we showed dramatic impacts. We're talking over a volt improvement in the transient response, both in simulation and measurement. We actually built it with some of their laminate systems included in a stack up for a 2000 amp board. And we were just running 1000 amp transients. And we're seeing over a volt improvement with their laminate in the stack. And so these are the challenges that we're dealing with. There's a lot of talk right now on vertical and horizontal, or I like to say lateral power delivery. And so there's a lot of people who are moving towards vertical. And I know Steve and Heidi and I talk about this all the time. And we don't see a good answer on to why people move to vertical. In fact, what we're going to probably work on later this year for another DesignCon paper is showing that horizontal is definitely not dead, and that really this is really what it's going to be in the future based on what's coming from new capacitor technologies to new laminate systems to how you integrate these. Because really state of the art for these high power systems, most of these VRMs out there, really 2000 amps is still the limit, right? I mean, there are solutions that are running at greater than 32 phases, like 64 phases, but those aren't really public. And so there are a lot of challenges right now just to scale, because these ASICs, the density is just going up and up and up. And we're just adding more and more SerDes, more and more memory buses. So to model these and really sign off everything, the challenges become enormous. And so for us as a service provider in a products business, where we are attacking that is trying to be faster, finding solutions to, one, be right, finding solutions to help increase the speed from the simulation and optimize that. And Tyler's going to talk about one of those today, and showing how we can be right and be confident that we're doing it right.
Yeah, I'd like to get into the thick board aspect here for a moment. Back in 2020, I worked on a few backplanes for a mil aero company, and those bad boys were 6.5 millimeters thick.
Sure.
And I told a few people about it, including Rick Hartley, and his reaction was, "Whoa, that's a thick backplane!" And now I'm looking at 3U VPX cards that are 2.5 millimeters thick, and I'm like, this is a thin card considering the number of layers and the amount of stuff they're trying to pack in. And you mentioned how this impacts the inductance, and I think particularly for backside power delivery. So tell us a little bit about how the thicker boards are impacting everything, I guess, both for SI and PI, right? Because for backside power delivery, right, you got a longer total path for current that has to flow into the chip, and so that's going to impact the inductance. But what about for SI?
Yeah, I mean, for SI, if you look at depending on how the design is done, what we see a lot of people doing, they're doing their fan out on those upper layers, right? And then they're just basically routing those down. In fact, what we try to get a lot of our customers to do is to do their fan out, but minimize that, so that way you can use your upper layers for the high current power routing. especially for an HDI board, which if you're doing a data center board, it's already automatically going to be HDI. It's rare, very rare, unless it's a very cost sensitive sort of application. And those are few and far between from what we've seen. We work with a lot of data center, ATE, semiconductor companies. Most everybody's doing some sort of HDI design. And so putting the power layers as close as possible as the ASIC is really what's going to drop your loop inductance. Versus if you're putting it in the center, now you have this big loop, right? And so if you have any caps top side or bottom side, they have to go through this loop and back, and you need to look at that total loop. And what we show, and in fact, we have another tool that we'll talk about with you probably later in another podcast, where we show quick analysis where we can take an EM extraction and set thresholds, and we can tell you if you could install that cap on your PDN or not, and if it's even doing anything for you just off the bat. Because we're looking at those sort of things. And we show this all the time with our customers, because a lot of customers will put all these caps, and then we look at it from a different way and say, look, man, you cannot install this cap and you wouldn't see a difference in the transient response, I promise. And I can show it to you. And we do this a lot for a lot of our customers. And when we show them, they're like, holy cow. And it's because of where you routed it, what structure you use. And so these are the challenges. Heat's another problem. That's another problem we see, right? So this is a constant thing. So we're talking with folks at Qnity, right? So just to give you some context, right, because Qnity is kind of a newer name. DuPont spun out their electronics laminate business, and then they rebranded as Qnity. So for everybody on the podcast, just to be aware. So it's Qnity Electronics now. And so they make all these laminates, right? And so they have these really thin laminates. They also have like a thermal laminate. And so, but if you're using a really thin laminate with 3-ounce copper, you can spread that heat and then just use the right cold or hot plate or heat sink to pull that heat out. And so these are their challenges we see. You have these crazy ASICs and power supplies managing that heat. And that's another reason why I say vertical is way more challenging. Now you just went from top side cooling to top and bottom side cooling. And if you're routing, again, vertical, so you have all this high current going through your entire board. So you have all these vertical structures that are now potentially antennas that can couple to every signal layer in your entire design. Does that make any sense? Doesn't to me. And so we plan to do some things where we've built some fixtures. We're going to be building some more, and we're going to be showing models and measurements and showing really the benefits of one versus the other to kind of look at this from a quantitative approach to really explore how to make one better than the other while adding in some of the latest laminate systems, some advanced systems that are out there that people aren't aware of and that are coming to light, as well as some of the new capacitor solutions. We're working with capacitors from vendors that are sub 40 picohenries and down to sub 10 picohenries. Just to give you an idea here of what that means, an O201 cap typically is around maybe 120 picohenries from an ESL perspective. And I'm talking about a cap that's sub 40 at 70 microfarads. And I have another cap on my bench that I measured that's sub 10 picohenries, and it's 1200 microfarads with an ESR in the hundreds of microohms.
Very nice.
So the point is there are solutions out there that completely blow away what's available, and it'll allow integrators to really challenge these problems and build solutions that they couldn't conceive.
Now, you mentioned something interesting here, and I think this will be the last kind of technical question before we start to get into what you're doing with simulation. But you mentioned something interesting here with you could show that you can depopulate a particular capacitor in, let's say, your PDN and prove that this actually doesn't do anything. I feel like a lot of designers, whether they're doing the PCB or they're just kind of the EE doing the front end, they just guess. They just kind of, maybe they had a tool where they were able to look at the PDN impedance and they said, well, I have to throw this ridiculously large number of caps at it, but eventually it gets, low enough. So we're just going to go with it. Right.
Yeah.
Is that the approach that you see, and you're kind of able to prove that that's a suboptimal way to go?
It is. And we still see people, and you've talked about this on some of your YouTube videos, I know, and some of your podcasts, people are still routing traces to caps. Yep. Whereas guys like Rick Hartley, Lee Ritchie, and others have been preaching for years via impact. And I see a lot of people copying that same content and reposting it, like on LinkedIn, yet you still see this propagated. And I look at that, just even a simple layout review, like, why did you do this? When we just put the VIA in pad. You already have VIA right here, just move the VIA here. And
Yeah.
you just dropped that alone. I mean, you can think of it this way. A post-it note thickness is around 30 picohenries, 30, 40 picohenries. And so if you move it a few mils, right, you just dropped 100 picohenries.
Mm-hmm.
It's all about the inductance at the end of the day, which is kind of why our logo has a big inductor in it.
Right. I just noticed that now that you say it. It's right there in the background. All right, let's go ahead and transition into maybe what you guys are doing for SI analysis, because I think that's really cool, and you guys are going to show us something really interesting here today on the podcast. And before we get into this, I'd like to note that anyone listening on audio, please head over to the YouTube channel and make sure to tune in there, and you'll be able to see one of the demos that we're going to run in this episode. So if you could, tell us some of the challenges you've identified and that folks are probably very familiar with when it comes to SI analysis for large parallel buses like DDR. Maybe Tyler, you want to take that?
Sure. I mean, definitely one of the challenges for us, like running the simulation and then giving the results to the customer, is that we're handing them tons of data to look at. You know, the original reports we were giving them from the ADS tool, it'd be like a long PDF and just a table of pass-fail with not much else to it. So it'd be difficult to identify any trends, like what causes it to fail or which signals are worst, kind of thing. Also, how long it takes to run these simulations and to run a compliance could be a lot of time. And setting them up also takes a lot of time. So mainly it's things that take a lot of time and managing tons of data.
Yeah, Zach, to kind of complement, we are big memory designer users on the ADS side. We love Keysight ADS. We're huge ADS users. Tyler is a Keysight certified expert. I'm a certified expert. But the compliance flow is challenging. And so we've been working really closely with Keysight, and we built this flow to complement the ADS Memory Designer compliance flow. So you would still take a waveform from Memory Designer, and then you just put it in our tool. And the way the flow used to work, it would take anywhere from 24 hours to 4 days to run a complete full bus simulation for a DDR4, DDR5, or LPDDR simulation, full compliance to the JEDEC standard. And we would get false positives, and we would work with customers, and we could prove that there were false positives when we go through the raw waveform data. And we had customers saying, we can't have that, you got to turn that off. And we're just like, okay. I'm telling you, we work with some of the biggest memory companies in the world. There's really only three: Samsung, SK, Micron. We work with them, and they're telling us they can't have false positives. And so we worked with Keysight, and we came up with this tool, and we're launching this with them to basically complement the workflow. And instead of taking 24 hours or 4 days to run our compliance, you take the waveform data, and it's done in under a minute.
So why does it take so long? Is it just because you're running full wave 3D EM simulations on the actual bus as it's laid out in the PCB, or is there something else?
It's the way the workflow is set up, right? So part of the challenge with the way Keysight has it set up is ADS will, well, first off, what they're doing is the compliance app is from the scope side. So it's from the equipment piece. And so you have to run their offline scope. So if you want to run any sort of DDR, LPDR compliance, you're running basically the native app that would run on the oscilloscope. And so what ADS does is there is a plugin that is built into ADS that calls Infinium Offline, which you have to have installed. And then Infinium Offline will launch the respective compliance app, which you also have to have installed. And it's going to run that, but the way it's running a full simulation that you already ran. So if you already ran the simulation, you already have the waveform data, but it's running again. And so what we do is we just store that data as part of our process flow, and we can have people give us this. And it's not going to have to run all the compliance checks, because we just want that raw waveform data, and we can add the right leveling and do all those pieces that are needed as required, depending on the simulation that we're trying to do or the standard. And what Tyler and Signal Edge team have done is built all that into the tool. So it's a very easy step and process and check. And so if you want to run corners and have all those waveforms and you want to check compliance on multiple corners, so you're looking at, typical min max or fast and slow, you can load all those in the tool and just have one report that's checking compliance on all those waveforms to assess your overall performance across all the performance corners of your entire platform, which is a huge time saver. And so what ADS does is it's running this waveform and it's running through the compliance, and it's painfully slow. I don't know why it's painfully slow. I've asked for them to run it in parallel and, tried to run it on HPC. We've done all sorts of things. We never could get that to work. The last piece that's really painful is that when you run this compliance flow, you lose your computer. It steals your mouse. And that's the worst. So we would always have to run it on a VM. So that way we can, minimize that VM so we wouldn't lose that hardware asset. So not only do we lose a license, but we lose our PC, so we lose an asset. So this was all very painful. So what we did is we made a tool that ultimately complements the workflow, but gives customers back the speed that they want. Where you're not waiting 24 or 48 or 4 days to get data to check if you're pass fail. You're getting it in a second. And you're able to quickly go back in the layout and tweak it and iterate and then run it and extract and run it again.
Yeah, this was born out of necessity. We'd have customers with designs that have 5 interfaces, and they want to see the CAC simulation, the data write and read simulation, and then across fast, typical, and slow. So that's 9 different simulations. To run compliant on it could take at least 9 days, maybe up to a couple weeks.
Yeah, there's I think some folks who don't do these kinds of simulations probably aren't familiar with a couple of things, right? First of all, just the sheer number of signals that you have to simulate in some of these systems that you're talking about. I mean, you're mentioning 5 interfaces here, but then also how to work with some of the model inputs. And Ben, you mentioned the corner cases. If you could, for folks who aren't familiar, just explain what that means.
Yeah, sure. That's a good point, Zach. So when you're running simulation, right? Typically, when you set up an IBIS model for simulation where you have a memory controller on one side of the bus, now we're talking specifically memory, and this could be, say, DDR4, DDR5, LPDDR4, LPDDR5, etc. It doesn't matter. You have a memory controller on one side. That could be an FPGA, it could be some custom ASIC, or a microcontroller, depending on what's built in. And so then on the other side, you have the memory, some sort of SD-RAM. And you have another IBIS model for that. And so now you have a bus, and there's multiple nets between the controller and each DRAM. And so, for instance, on a DDR4, if you have 9 byte lanes, where each byte lane is 8 bits, if you're doing by 8, right, you'd have, and 72 includes full ECC, that means you have 8 byte lanes plus ECC, or 9 total byte lanes. Then you also have a data mask bit for each byte lane, a strobe, and then all your command address, and depending on how you configure it, it's usually around 27 command address nets. So you do the math, you're well over 100 plus nets, right, for a full DQ CAC simulation. And so when we're running these corners, right, you want to look at the system across temperature, depending on where you're operating. Because, some applications could be data center, some applications could be medical, aerospace, defense. And this is very common in those industries where you're going to run at the corners. And what happens is in the IBIS model, and the IBIS standard has this all built in, you have different slew rates based on those corners. Sometimes you have different drive settings based on those corners. And so what happens is your eye may look great at one corner, but you run it on a slow corner, your slew rate is different. And so you might have an issue. Or you might have overshoot on a fast corner, and that could be creating ringing and other ISI problems that you need to mitigate. And so this is why you simulate that, because depending on the silicon, right, because silicon is built, but I'll tell you for a fact, right, if you work in the industry, a lot of these companies, like when they work with ATE, they're doing some sort of percentage of testing. And so let's just say they test, but they find that this one is not meeting the same performance. Well, they're going to sell that as a lower quality piece ASIC, but they're still going to sell it because they don't want to lose that yield. And then if they have one that's higher performance, and so this is where these corners come in. And so you want to model for that to assess those corners, not just from a yield perspective, but from a temperature and operating perspective. And that's what's built into these IBIS models.
Right, that makes a lot of sense. This is basically like kind of like a worst case analysis where you're looking at what is possible in those cases that may not be common, but the customer could still experience it in their system.
Yeah.
Yeah, and passing the slow and the fast corners tells you you've got some margin in your design too, for the
Sure.
typical cases.
Sure. So this should, I think, highlight the challenge with kind of the traditional approach for qualification and verification in something like DDR. It's not just that you have, however many signals, right, plus all the DQ strobes and then the data mask and all the ingest and control lines. It's that you have to run it multiple times for all these edge cases if you really want to understand what the potential risks are in a given design.
Both for read and write.
Right, yes.
Robust, so you got to look at it each way. Because the drive strength for a DRAM is not the same as a memory controller. They're never the same.
Sure.
And so you're going to see very great differences. And so you might look great going one way on a write. You might look completely different going the other way on a read.
That's a great point. And actually, it brings up, I guess, another question here. There's something that you and I spoke about on one of your previous podcast appearances, Ben, which is model quality. And we were talking about this specifically in terms of power integrity, but I'm wondering if there's also a model quality issue here with like IBIS models and signal integrity on each end of the bus, right? Because it is a bidirectional bus. So you'd have to have a good model for the DDR chip and then also a good model for whatever the system host is.
Yeah, and there are issues with that. That's a whole nother conversation, and we've talked about that. There are definitely fundamental issues. I will tell you, Randy Wolf being the past president of the IBIS forum, he was at Micron until recently. Now I think he's at Siemens. He's really set the bar for what IBIS models should be coming out of Micron when he was there. If you pull down any Micron sort of IBIS model, you're going to get an IBIS quality report. And you get everything. And so you can be almost assured that that model has been checked to a T. However, with other vendor models, you're not going to get that. And in fact, you should demand it. Because if you get an IBIS model, how do you know it's been checked? And what's it been checked against? There's a couple ways to check it. Typically, what most people are doing is they're taking the raw SPICE model that they pulled from silicon, and then they will overlay that against the IBIS model they created. And they're checking it at the different corners. However, not everybody does that. It comes down to everybody trying to do more with less, cutting corners, process, etc. And so this is where sometimes you have issues. We see issues all the time. We see like a weird like glitch or non-monotonic behavior in the waveform. And what happens is that when they extracted the voltage and time waveform, they made an issue where they skipped a couple steps, and now you created this non-monotonic behavior that's not real. And so these are things, this is why you need to check the IBIS models. I encourage everybody, and I teach everybody, go in there, look at it, look at the waveforms. These tools out there that are free that you can look at, or you can just plot them in a CSV, Excel, or you can write a Python script to do it. Point is there's tons of stuff out there for you, and there's no reason to not check before you just hit simulate. No reason.
Sure, that makes perfect sense. So I think maybe without further ado, we can get right into what exactly your tool does, what it looks like, and how folks can, or what folks can expect when they get access. So I think, Tyler, that's where you take over. And just to be clear, because I'm sure someone is going to hop into the comments and bring it up, there's no AI involved here.
Right.
Well,
Yeah,
thank goodness.
Yeah. All right, so I'm going to launch the tool. We're calling it MEM Check Pro to kind of align with another one of our products called StepLoad Pro. The first step here is to load all of your data, so all of your waveform data. And I'm just going to skip some steps and load my 9 data sets. So these 9 data sets, I've got the command address controlled simulation data out of ADS. One of the first things the tool will do is convert the ADS data set, or whatever data set. It could be coming from oscilloscope measurements or some other simulator. It converts it to a common form that the tool is going to process, and it stores that in an H5 or HDF5 format, which is just compressed format for lots of data. So that's what you see here. So I've got typical slow and fast for command address control, data write, and data read. So 9 data sets to cover an entire interface.
Now, when you say 9 data sets, would this be like 9 byte lanes, or what
Yeah.
exactly is one of the data sets?
This is 9 different simulations.
Okay.
So for the command address and control, it's the about 27 signals from your controller to 5 different DRAMs. This one has 5 DRAMs because it's a 72-bit bus. And then for the data writes and reads, it's going to be the 72 bits of DQ and was it 9 bits of the strobe and the data mask. So here's the compliance tab. From here, you can select which compliance tests you want to run, and it defaults to everything enabled. You can run one thing individually, but it runs just as fast running all of it. So we're processing 9 data sets here, where this could take days on the Infinium tool, and it's going to take less than a minute here. So we've got all of our results across fast, typical, and slow. So I could go in here. So I see you've got a DQS to CK timing issue. That's because I know this simulation data didn't have write leveling applied. So if I wanted to do a post-process write leveling just to see what I've got, I can apply it here and then rerun that. And then I'll see that it passes. So all it's doing is just taking the clock waveform and the strobe waveforms and aligning them in time. So a 0 phase offset, basically.
So just again to reiterate, this type of analysis to determine this pass-fail condition that you're displaying in the results table, normally that would take many dozens of hours or days in order to get to this point.
For one data set.
Right. And we're literally running it here in seconds live on YouTube. And I encourage, again, anyone who's listening on audio to head over to YouTube to watch this.
Yeah, it gives you goosebumps, right?
Yeah.
We're taking advantage of some parallel processing and some new techniques. And then the thing we give to our customers has been this HTML report, which it's generating now. We would give our customer a report like this.
Sure.
It tells them what failed, what corner it failed at, all the passing results, what's there for informational, what wasn't run. But you get a lot of data from this compliance test. So I've been really trying to find ways to make that data easily to digest. So let me find a good plot here. So looking at the input high and input low levels relative to the AC limits that are defined in the JEDEC standard, you can see at each of the DRAMs where the clock input levels are. So you see the highs on the top of the chart and the lows here. Also grayed out are the slow, typical, and fast results. So you kind of get everything in one view. Yeah, so these kind of timing tables and voltage all kind of summarize the specs listed in the compliance or the JEDEC standard. But we typically look at on the DDR4 analysis are the eyes. So we're also plotting all the eyes with the JEDEC mask here, and you can filter it by signal or DRAM, whatever you want to see, scale the size. But we also summarize everything in this single chart here. On the x-axis, you get the time margin, and the y-axis gives you the voltage margin. So you can see distribution of all of the eyes, the eye margin at each of the DRAMs for each of the signals, and also grayed out, we're just kind of giving you an idea of how it performs across the corners. So slow, typical, and fast. So if you had some kind of outlier way out here, you can see what's that signal. If I hover over it, it'll tell me what signal it is. And then maybe I'll go look at the artwork and see what makes this one different than the others. So I see I have some monotonicity failures here for some of the command edge control signals. So A6 at U600 is one. And I see I have one violation here. At this one edge is just barely non-monotonic. And I think at the fast corner, it's even a little more pronounced.
the risk here with non-monotonicity is that you get an unintended toggle signal transition between the logic state.
Yeah, so this would be more of a concern on the clock signal, but for command addressing control, I might see, I've got tons of hold timing margin or tons of setup timing margin.
This is very cool. Thank you so much for going through this whole demo. And again, I encourage anyone who's listening on audio, head over to YouTube and take a look at this demo, and you'll be able to see this very cool tool in action, running all the simulation instantly, it feels like, in the span of a YouTube video. So Ben, you had mentioned earlier while we were talking that you have something else on the roadmap as far as simulation tools that you guys are working on. If you could, just give us maybe a sneak peek before we have you back on in the future.
I don't know if we're ready for a sneak peek, but what I can tell you is what we're
maybe a teaser, verbal teaser.
All right, what I can tell you what we're working on, because we build our own measurement-based models. We have full state-space average models. Well, what if I told you not only could we take your EM extraction and tell you if any of your layout needs to be changed based on any of your caps and routing and structures, or what if I told you we would automatically optimize your control loop, whether it's PM bus, non-PM bus, on the voltage regulator, and give you a full solution and do all that in a few seconds, and tell you if it's stable or not?
That's compelling for sure. I mean, especially when it comes to telling you if it's stable.
And telling you what cap to use to fix it anywhere.
There you go. That's even better, right? Because that's another one where I think people are going to end up guessing, or they iterate through a large number of values, and then trying to actually predict stability takes forever.
Yeah, we wouldn't just tell you what cap to use. We'd tell you the specific part number.
Oh, there you go. That's even better. So you've got the full library of caps, all their ESL values. You're able to say, okay, this is actually going to work at this frequency as a cap, and give you this much capacitance, and that's going to be what you need to fix your control loop.
Well, and this is the challenge, right? We talked about some of the challenges with the complexity of designs, ASICs, FPGAs. First was a great example for like a mid-tier, right? 200 amps sort of, or 100 amp sort of class PDN, depending on how you configure it. But even that, you have almost 30 power domains or more, depending on which package size you're using coming out of that BGA. And if you're trying to sign off all those per their data sheet, right, AMD's data sheet, it can be overwhelming and very time consuming. So people want faster. It's all about speed to market.
Yep. Yeah, I agree 100%. Well, I want to thank you both for being here today. We're running up on time, but as you guys develop more of this stuff, you have an open invitation to come back and show our audience, and I think folks are going to be pretty excited about this.
You can reach out to us at info@signaledgesolutions.com, and we're happy to talk to you.
Ben, Tyler, thank you so much for being here today and presenting what you've built. I'm very excited to see what you guys come up with in the future.
Our pleasure. Thanks for having me.
Thank you so much.
To everyone that's out there listening, we've been talking with Ben Dannan, founder of Signal Edge Solutions, and Tyler Huddleston, SI/PI engineer at Signal Edge Solutions. If you're watching on YouTube, make sure to hit the like button, hit the subscribe button. You'll be able to keep up with all of our podcast episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.